Right now, a fault that runs straight toward San Francisco has ruptured twice in 5 weeks. Almost nobody noticed because every camera on Earth was pointed at Japan. The U.S. Geological Survey didn't call it an aftershock. It called it a potential main shock. Stay with me because by the end of this you'll know the exact signal that tells us whether that word potential is about to become something far worse. At 7:40 p.m. on Tuesday, July 28, 2026 Pacific Daylight Time, the ground shifted about 8 kilometers east-southeast of Cloverdale, California. The USGS logged it at magnitude 4.3, revised upward within the hour from an initial 4.2. The rupture sat roughly 5.5 kilometers down, a little over 3 miles, shallow enough to count as almost skin-deep in earthquake terms, and shallow ruptures shake harder for their size because the energy travels through less rock before reaching your feet. Nobody died, nothing collapsed. The USGS's automated damage model returned a green alert, its lowest possible category. More than 520 people filed felt reports, from towns close to the epicenter like Healdsburg and Geyserville, and from places absurdly far away, Sacramento, the Bay Area, even Nevada, over 160 kilometers out. The strongest shaking measured around intensity 5 on the modified Mercalli scale. Dishes rattled, pictures tilted. That's the entire physical damage report. On paper, this should have been a nothing story. A magnitude 4.3 in Northern California on an ordinary week gets 100 words and disappears by morning. This one didn't disappear, and it has nothing to do with how hard the ground shook. It has to do with what happened immediately after. Within hours, the USGS's sequence tracking system had logged more than 160 separate seismic events tied to that single rupture, a number that kept climbing past 162 through the night. That figure is the single most important number in this entire story, and almost nobody outside seismology ever saw it. Here's why. Aftershock counts scale with the size of the main shock. For a magnitude 4.3, the textbook expectation is a small cluster, maybe a dozen aftershocks, fading within a day or two, like ripples settling in a pond. A sequence of over 160 events is roughly 10 to 15 times that. When one small locked patch fails and resettles, you get a quiet, contained sequence. When a much larger volume of crust is already sitting close to its own breaking point, and one piece of it lets go, the redistributed stress can light up everything nearby. This wasn't one patch failing quietly. It looked like a section of California's crust actively reorganizing itself. The USGS's own forecast put the odds at roughly 28% for at least one additional magnitude 3.0 or larger aftershock within the following week, a window that opened Tuesday night and is only now closing. None of this would matter as much if it happened somewhere geologically boring. It didn't. The Cloverdale epicenter sits directly on the Maacama fault, a name almost nobody outside working seismology has ever heard, running like a hidden seam through wine country toward one of the most densely populated regions in America. The Maacama is a right lateral strike-slip fault, running northwest to southeast through the Coast Ranges east of its far more famous cousin, the San Andreas. It slips at roughly 9 millimeters per year, according to the deformation model built for the 2023 National Seismic Hazard Model. For comparison, the offshore San Andreas nearby moves at around 24 millimeters a year, nearly 3 times faster, and yet that section has produced almost no cataloged earthquakes at all. Speed alone doesn't predict danger. Sometimes the quiet fault is the one worth watching. Part of what makes the Maacama deceptive is that it creeps, meaning the two sides slide past each other slowly and continuously without triggering an earthquake, like a door swinging shut so slowly you never hear it click. That creep rate runs between 2 and 6 millimeters a year. Slow enough you'd never feel it. fast enough to measurably offset curbs and roads that cross the fault trace. How do you know if a slow-moving door is quietly closing safely or building toward a slam? Public intuition treats creeps like a pressure valve, quietly bleeding off danger. That intuition is incomplete. Researchers studying this exact fault have said so directly. Creep relieves some strain, but strain is still accumulating. If the fault moves about 9 millimeters a year total, and creep only accounts for 2 to 6 of those millimeters, then somewhere between 3 and 7 millimeters a year isn't being released peacefully at all. That leftover motion stores itself as an elastic strain in the surrounding rock. It doesn't evaporate. It waits. And this wasn't Maacama's first move this summer. On June 24, 2026, at 8:10 a.m. local time, a magnitude 5.6 earthquake tore loose near Ukiah in Mendocino County, its epicenter almost directly beneath the Abhayagiri Buddhist monastery, the largest earthquake this fault has ever produced in its entire 9-decade instrumental record. Seismometers within 10 kilometers recorded intensities between 5 and nearly 6. The USGS estimated roughly 10,000 people experienced intensity 7 shaking. More than 4,500 felt reports poured in. Thousands lost power. There was minor damage, and there were injuries. On the logarithmic magnitude scale, each full step releases about 30 times more energy than the one below it, meaning this single event was roughly 30 times more powerful than anything this fault had ever produced before. Line it up. June 24th, the Maacama's largest recorded earthquake ever. 34 days later, a magnitude 4.3 with an aftershock sequence 10 to 15 times larger than expected, 55 kilometers to the south-southeast on the same structural trend. Two remarkable events, 5 weeks apart, on a fault that had never before topped magnitude 5.6 in the modern record. That doesn't guarantee something bigger is coming. California's instrumental catalog only stretches back about 150 years, a blink in geological time, and short catalogs can manufacture patterns that are really just noise. What it does mean is that a fault most people have never heard of has, twice in 5 weeks, made it unmistakably clear it's active. June's earthquake also delivered an uncomfortable lesson about earthquake early warning technology. Shake Alert, the system covering the entire West Coast, functioned exactly as engineered, detecting the rupture and issuing alerts. But researchers were blunt about the physics. Systems like Shake Alert are detectors, not predictors, and they can never give meaningful warning time to anyone standing directly above the rupture. The alert travels at the speed of light. The destructive waves travel at a few kilometers per second. 30 seconds of warning in San Francisco, hundreds of kilometers from a distant quake, can save lives. Standing right on the fault, that math cannot be won. While studying June's aftershocks, seismologists found something they couldn't immediately explain: a tight, linear band of small earthquakes strung between the Maacama and the neighboring Bartlett Springs Fault, the unmistakable signature of an active structure. But it doesn't officially exist. It isn't listed in the National Quaternary Fault and Fault Database, America's authoritative inventory of active faults. California's own state mapping shows structures there, but labels them pre-quaternary, presumed inactive. Seismologists eventually crowdsourced an answer, pointing to a 2013 paper in the journal Geology describing the same structure. There's an active fault sitting inside California's coast ranges that isn't fully accounted for in the country's official map. Not hidden, not covered up, just unnamed. The Maacama's deeper history stretches further back than any seismometer ever could. Buried sediment layers near the town of Willits show offsets consistent with several major earthquakes on this fault within roughly the last 2,300 years. Researchers avoided assigning precise magnitudes to that evidence, since converting a single buried offset into an exact number isn't defensible science. But their informal estimate placed those earlier ruptures around magnitude 6.5 to 7, possibly larger, reasoning that smaller earthquakes rarely leave a fingerprint that survives over 2 millennia buried in soil. A magnitude 6.6 alone releases roughly 30 times the energy of June's 5.6. A fault that creeps continuously and still produces ruptures like that in its buried record is a fault where creep is clearly not doing the whole job. Follow the Maacama's trend southeast, and this stops being abstract. The Rogers Creek Fault picks up in roughly the same region as this summer's activity and runs southeast through Santa Rosa toward the Bay Area. For decades, nobody knew what happened to it once it reached San Pablo Bay. In 2016, subsurface imaging led by USGS researchers, published in Science Advances, finally answered it. The Rogers Creek Fault and the Hayward Fault are physically connected beneath the bay, bending roughly 10 degrees where they meet, forming one continuous structure stretching about 190 kilometers, roughly 118 miles, longer than the distance from Los Angeles to San Diego. The maximum modeled magnitude for a rupture along that full combined length comes out to roughly 7.4. That number needs an immediate caveat. Ruptures spanning two connected segments at once are real, documented elsewhere on Earth, but rarer than single-segment ruptures. The full 7.4 scenario is considered less likely than the Hayward Fault rupturing alone, modeled separately at roughly magnitude 6.8 to 7.0, a scenario that already sits on the short list of America's most dangerous earthquake risks, because the Hayward Fault runs directly beneath the densely populated East Bay. A full 7.4 rupture along the combined system would release roughly 700 times the energy of June's magnitude 5.6 near Ukiah. To be precise about what is and isn't being claimed, a magnitude 4.3 near Cloverdale does not physically stress the Hayward Fault. There's no known mechanism for that, given the distance. The connection here is structural, not causal. This summer's activity sits at the northern tip of a single continuous fault system running into the most densely populated corridor in Northern California, a system whose buried record already runs roughly 2 full magnitude steps larger than anything in its modern catalog. One clarification: a second, unrelated cluster of small earthquakes appears on the same regional map, near Clear Lake and the geysers, the largest geothermal field on Earth. Steam extraction there causes small induced earthquakes, well documented and confined to the reservoir itself. The Cloverdale sequence sits on the Maacama structure proper, and June's larger rupture occurred more than 55 kilometers northwest of the geothermal field. Two different processes sharing the same map view. Here's likely the real reason this story slipped past almost everyone. Roughly 27 hours before Cloverdale, at 4 p.m. Japan time on Tuesday, a shallow crustal earthquake ruptured beneath Kumamoto Prefecture on Kyushu. Japan's meteorological agency measured it at magnitude 7.1. The USGS's revised moment magnitude came out at 6.8. It struck inland, not along the offshore subduction zone, at roughly 10 kilometers depth, registering the maximum reading on Japan's intensity scale, Shindo 7, in Uki City and Hikawa Town, only the second time that's happened since the Noto Peninsula earthquake in January 2024. A tsunami advisory went out within 2 minutes, forecasting waves up to 1 meter, lifted 2 hours later with no destructive waves. The damage on land was severe, at least one confirmed death. 20 to 30 employees initially unaccounted for at a Kumamoto City shopping mall where the second floor caved in, followed an hour later by an explosion that blew out walls and exposed the steel frame, witnesses reporting the smell of gas beforehand. That mall had reopened only 6 weeks earlier, rebuilt after Kumamoto's previous earthquake in 2016. More than 90 people were reported wounded. Roughly 300,000 were directed to evacuation centers. Sections of the Kyushu Expressway split apart, and part of the historic wall around Kumamoto Castle collapsed for the second time in a decade. Japan also provides the clearest case study for why California's sequence deserves attention, from this exact same region. On April 14, 2016, a magnitude 6.5 earthquake struck the Futagawa and Hainagu faults beneath Kumamoto. Emergency crews treated it as the main event. People moved back into buildings that seemed to be standing. 28 hours later, a magnitude 7.3 struck the exact same fault system. The first quake was only reclassified as a foreshock after the second one arrived. Both produced Shindo 7 shaking. 28 hours was the entire distance between "this is over" and "this was only the beginning." How do you warn people about an earthquake that hasn't decided yet whether it's the beginning or the end? This is exactly why the USGS's word choice for Cloverdale matters. Calling a magnitude 4.3 a potential main shock isn't hedging. It's an honest admission of a real scientific limitation. No instrument, no signature tells you whether an earthquake is a foreshock or a main shock at the moment it happens. That classification only ever exists in hindsight. The base rates are genuinely reassuring, up to a point. Something larger follows within 3 days roughly 6% of the time, within a week roughly 5% of the time, and that probability barely shifts across the magnitude 3 to 5 range. 19 times out of 20, nothing larger comes. A magnitude 4.3 like Cloverdale's is roughly 95% likely to be the biggest event of its own sequence. But the reason to keep watching isn't that the 5% scenario is likely. It's that nobody can currently identify it in advance. In Kumamoto, it was identified 28 hours too late. In 2011, the magnitude 9.0 Tohoku earthquake was itself preceded 2 days earlier by a magnitude 7.3 that nobody flagged as a warning either. Japan's meteorological agency is applying that exact lesson now, warning of strong aftershocks for up to a week, with the highest risk concentrated in the first 2 to 3 days, a window closing right around now. Japan's Prime Minister has told residents in the hardest-hit areas to prepare for another quake of similar size, standard protocol that exists in this form specifically because of 2016. There's one genuinely useful diagnostic here, and it works identically in Sonoma County or Kumamoto Prefecture. The number that matters isn't the next single magnitude. It's the shape of the aftershocks on a map. If they stay clustered tightly around the original rupture, that's a sequence gradually decaying, releasing local stress the way textbooks predict. If the cluster starts stretching outward along the fault's trend instead, that's stress physically transferring onto the next segment, and segment-to-segment transfer is precisely the mechanism by which a moderate sequence can occasionally evolve into something considerably larger. Somewhere beneath the vineyards and quiet backroads of Sonoma and Mendocino counties, a fault most residents have never once thought about has spent 5 weeks trying to get the world's attention. Twice, while every camera on the planet pointed somewhere else. It didn't ask for coverage. It simply did what faults have always done, quietly, for millions of years before a single human city stood in its way. Whether this sequence fades into the same silence it came from, or becomes the opening paragraph of something much larger, isn't a promise anyone can make today. But you now know exactly which number to watch and why the ground under Northern California has been trying to say something the entire time. Subscribe if you want to see whether it finishes that sentence, because the next signal won't come with a headline. It'll arrive quietly in a data feed almost nobody else is watching.